Hello and welcome back to another episode of the Oxford Online Maths Club. Just me on the stream today, but also all of you here in chat. There's a reason it's just me, which we'll get to at some point. I'm going to try and get my computer to do lots of stuff, and I thought I'd give the computer a break from not also being in a Zoom call. Right, how's your day going? How's everyone at home? Let's turn the poll on for Slido. If it's your first time joining us, do say hi in the Slido chat if you want to. And there's a poll where you can let us know, on a scale from 1 to 5, how's your day been? I've had a very confusing day, so I'm looking forward to a bit of Maths Club where, well, we'll see how confusing that is as well. Maybe my confusing day will get more confusing. Good. Okay. While people are joining in at home, I think I'll try to say a little bit about what I'm up to. I've got a kind of big topic, waves, and the thumbnail, which you might have clicked on to get here, has got 4 emoji in of different places where waves turn up. The idea is that waves turn up in all these different places, but from a mathematician's point of view, there's an equation that underlies a lot of different applications, a lot of different things. And I know that some people maybe aren't here for applied mathematics, aren't here for like physics or applications. But the good news is that mathematicians study the kind of underlying structures and equations, and then the applications, you can think of those as kind of coming for free afterwards. Herb says that Slido is new and shiny, which is a little bit scary to me. It's currently working, the integration is going okay. If Slido does something too new and shiny, then if Slido all disappears, then you can find us on the Maths Club website, which is at maths.org.au. Oh my goodness. Which is on screen in the bottom corner. What a confusing day. Hi, anonymous people. Quick shout out to chat. Who else can I see? Mike is here, and Trish, and some anonymous people who say hi. Somebody asked if Maths Club is going to run for 10 years or even 100 years. I mean, we're going to do it one episode at a time. The icons are different. That's interesting to me. Okay. Chat has voted. And yeah, Olaf says that Slido is roughly the same on mobile. Okay, this is good. This is good feedback, aren't I? Neither says we're trying to work out how Slido goes together. Cool. People have voted for about, what is that, about 3 on the scale of how good was your day? 3.8, which is okay, but this is a weird bimodal thing. People don't want to pick 4. People picked 4 last time, but then the average is about 4. So it's one of those cases where the average, the mean average is not the mode at all. And it's also not even a particularly popular option. Right, good. Something about statistics there. Anyway, right, cool. Okay, I've enjoyed that a lot. Okay, so my aim is to try and tell you about the wave equation, or maybe just Laplace's equation. But there's some challenges between me and explaining those to you, which I think we'll get to. Oh goodness. Hello, anonymous person. Hi, that is a tough question about further maths grade boundaries. I've no idea. I imagine it's because they've got different questions on different exam papers. But yep, I'm not involved in, I mean, luckily for me, I'm not involved in any of that CAIE. Yeah, goodness me. Yeah, goodness, scores and stuff. Right, okay. Hi to Holly as well, who's just joined. The icons are different. Herb's onto something here. The icons are different. Like Holly gets 2 initials in there. Before, I think Holly would only have got 1 initial. Is this a new Slido feature? Hi Holly, by the way. Sorry to draw so much attention to your 2 initials, which is not a weird thing. Right, okay, let's get to some maths. So I think in maybe A-level mechanics or something, or maybe a physics class for all I know, you learn about waves on a string. You learn about the different ways that you can set up oscillations on a string that look like this. And they go up and down. 1, twang, up and down. And my memory of A-level physics and maybe maths mechanics units is that you're told that these are something like sine times nx, where maybe this end is at 0 and this end is at pi. And you're just told that they're these, and they're called harmonics or something. Does any of this line up with things that you've heard in school? Is this something you've heard about, where you have like different values of n correspond to different, maybe they're called modes of oscillation, or different, they correspond to different frequencies, or things that kind of overtones? Maybe it's even in music theory that you learn about these kind of different waves. Am I making any sense? Jacob just says it's 2 pi, which now I've got to think about. Thanks. So if n is 1, then I get something that is 0 again at pi. So I think odd numbers is okay. I think I'm going to stick with it. People are learning about this in physics. Right, okay. I want to take it from where you currently are. What have you currently been told about, I don't know, why? Why would a string do that, right? Why would a string do sine waves? So I should say this is supposed to be for sort of n is 1, 2, 3, and so on, counting numbers. I guess you could put n equals 0 in, but if you put n equals 0 in, then you get 0 back again, and that's not particularly exciting. I guess that's the flat string before you've set up any waves on it. Yeah, I think I'm doing this as a challenge for chat to explain A-level physics to me, and then I explain university maths back to you, and we see how that matches up. I guess I'm looking for a Y. I'm going to try and draw more pictures to try and help jog people's memory of maybe learning about this in physics or something. I really think they say something like, so you could have the n equals 1 mode, looks like this, like that, or the n equals 2 mode I've drawn up there, but I'll draw it again. Whoop. Oh, this is good, I've got a little grid here. N equals 2. Then the n equals 3 one is hard to draw. Oh my goodness, am I going to get this right? And then down again. Oh, it's not very symmetric. Not very symmetric. I'm having another go. N equals 3. And so on. Request for Fourier transform. You want to learn, what is that? GMP lib. Is that yeah, Fermat style fast Fourier transform. We'll get close. Ooh, this textbook you've linked me to is exciting. It's from before being able to typeset a sigma sign, so it's got a kind of ASCII sigma sign. I'm just going to put that on stream quickly. There's a request in chat that we should learn this. I just want to okay, reading like bits and doing things in binary. This is kind of cool. Somebody's had to draw a sigma using ASCII. Great stuff. Tristan said something about stationary waves. Let's see. Jacob's got a good guess about differential equations relating to velocity. I've got something to say about that. Right, the superposition of a travelling wave. Right, let's break that down. So you've got a travelling wave and a reflected wave. So that sounds like, to me, somebody's told you about travelling waves first, and maybe they tell you there are things like this, sine of, I don't know, kx minus omega t or something, and sine in the other direction, maybe? Travelling wave and a travelling wave in the other direction? We're doing both, we're doing physics revision. Yeah, it's this sort of simple harmonic motion, right? And it feels like simple harmonic motion, the thing that springs do. The pause there was because I wasn't sure if bringing in a different bit of physics would be helpful or terrifying. Let me know in chat. We could do a poll. Springs, right? So a spring, you have maybe a mass of a spring that oscillates backwards and forwards, and that does something like a sine wave as well. There are no coincidences in mathematics. Why is that the case? That a mass on a spring would oscillate in kind of the same way as this shape on a string. I don't think they tell you at A level, so maybe this is fruitless me asking. Okay, so Shrish's suggestion is that I do think about this as travelling waves. I mean, I have further questions about travelling waves that maybe we can get into. I want to quickly show you a kind of university approach to this problem, kind of the key steps of how you would approach this at university. I'm hesitating a lot, there's some tricky stuff, it's a little bit harder than stuff I normally do on Maths Club. It is not as hard as Fermat style fast Fourier transform, which I just got a request for, but it's a little bit harder than other stuff I've done. Goes like this. The thing is, the picture of just sine nx just shows us at one moment of time. What we'd actually like to understand is where is each point on the string at for various values of x and t, x for space and t for time. And you don't get any problems at A level where things depend on space and time. It's kind of a function of two variables, I suppose. I guess you sometimes see functions of two variables just if you're doing some really complicated iteration sort of thing, or if you have a sequence of different functions or something, and then you maybe see something with two inputs. But yeah, it's like Herb says, you've got, in a way, at each fixed point x, what we're going to get at the end is at each fixed point x, there's a bit of string there at that point x that's going to oscillate backwards and forwards just like a mass on a spring. So it's kind of sinusoidal, like a sine curve, in space and also in time. I promise this links back to the travelling waves. That I saw everyone gave that a thumbs up in chat, so I promise this links back to your travelling waves. Let's meet the wave equation, and I'm going to try and break it down. It relates to expressions like this, where something depends on space and time, and it's a differential equation. It involves the derivatives of this thing, which is maybe not so surprising if you've seen simple harmonic motion, which is about how something moves over time. There's a kind of Newton's law, F equals ma, is a differential equation as well. It's relating together forces with acceleration, and the acceleration is the second derivative of your position. Maybe you know this, that you have sort of position and then velocity is the derivative of your position with respect to time, and then acceleration is the derivative of that. The next one is called jerk, and then there are names for the other ones later on as well. The wave equation is beautiful. It relates together derivatives of f. I've got to get this right, let's go. It relates together derivatives of f with respect to time. They're related to derivatives of f with respect to space. Right, several things, pause. Several weird things have appeared on screen. I will do them one at a time. This is the wave equation that I want to talk about. Firstly, there's derivatives. It's a differential equation. It's talking about the derivatives of this function. Because the function's got two inputs, space and time, a string depends on space and time. Because it's got two inputs, there's two things that I might mean when I say derivative. Now, you've seen these both in school, I think. You've seen space derivatives. Probably you don't even think of them as space derivatives, where you do d by dx. You've got something that depends on x, so you do d by dx. It's a normal thing when you're doing a tangent to a graph or something. You have y of x, you do d by dx, brilliant. And then maybe in a totally separate module or bit of your A-level, you have things that depend on time, like this simple harmonic motion thing that twangs backwards and forwards. That depends on time because, that's the independent variable, if you like. So then when you do derivatives over there, you do d by dt for time derivatives. And in A-level, the two things never meet. You either have a function of space, where you do space derivatives, or you have a function of time, where you do time derivatives. The exciting thing that happens at university is you have functions that depend on both space and time. It's not restricted to little bits of string, by the way. I can think of lots of things that depend on space and time. Maybe let me know in chat. I see. Snap, crackle, and pop. Well done, chat. Maybe let me know in chat. Can you think of something else that I don't know, depends on space and time? My favourite one is the weather. The weather depends on space and time. You get different sorts of weather in different places, but then also it evolves over time. So when somebody asks you, how's the weather changing? They usually mean a time derivative. But if you're on your way to work and you see, it was sunny at home, but now it's raining because I've got into Oxford, then you're kind of experiencing more of a space derivative. Anyway, yes, this is multivariable calculus is the name of this thing, where we've got multi for many variables, or these inputs into our function. And we're doing a little bit of calculus, just a little bit of calculus, because we're doing some derivatives. Yeah, heat transfer. Okay, so heat transfer is a suggestion of something that depends on space and time. If you get an ice cube out of the freezer or something, then near the ice cube it's pretty cold, but that changes over time as the ice cube melts, and it also varies over space. I guess the rest of the room cools down a little bit to heat up the ice cube. Oh, now I'm thinking about how freezers work. I've fallen into some sort of physics trap. If the freezer was containing the ice cube, was it already in? Let's not go there. Yes, heat transfer. Good suggestion. Holly says much harder to imagine, but correct. Gravity's got something to do with space and time as well. Harder equation. So I'm going to try and avoid gravity. It was very tempting to try and put gravity as one of the emoji in the thumbnail, right? Because gravity waves are a thing. I'm not sure it's really accurate for me to say they obey the same equation, and I'm not sure there's an emoji for gravity. Side quest for chat. If there's an emoji for gravity, let me know. There's a suggestion there about tetration, which I think is still someone, inventing new sorts of. I've seen that sequence before as well, actually. Snap, crackle, and pop. Right. Where is this fundamental circle in our vibrating spring? Yeah, I've seen 3 blue 1 brown videos like this, where he points at a pi, or a factor of pi, or a sine or something, and says, where's the circle? Then we find the circle. Am I going to be able to do that? I'm not sure. Okay. So, something really interesting about sine of n times x, or sine of kx, let's say. So then, sine kx is interesting because let's call it y for now. Y equals sine kx is interesting because c squared, if you do 2 x derivatives of sine kx, then, I can't actually remember when people learn this, at some point in A level, right? But when you do a derivative of sine, you get cosine. And if there's a k inside, then something like the chain rule means that you get a multiple of k outside. Hang on a minute. So this says if we do 2 x derivatives of sine kx, so this is going to be an equals to something. Okay, help me out. So we do a first one. Sine kx gives me k cos kx when I do a derivative, and then I hit it again, and I get minus k squared sine kx. If you've never seen how to differentiate sine and cosine, then I guess spoilers for some future maths you'll learn. And if you have, hopefully I've got the right sort of numbers. There's also this factor of c squared, which I think somebody called out as the speed of light. Here it's the speed not of light waves at the moment, it's the speed of waves on the string. I guess the point of this episode is that it could be light waves if you want it to be. Applications kind of come for free. So I'm going to write this and see if I can get away with that. Yeah, what's c squared? So c squared is, for now, c squared is just some number that's in the wave equation. It's some number at some speed to do with the string, and it is a speed. It's if you like, it's the speed that waves travel at, but I'm not really thinking about travelling waves at the moment, so let's not think about that too much. It's some sort of constant that's something to do with the wave, something to do with the string, sorry. One of the nice things about maths is you can treat these things as, there's a constant here, which, I don't know, maybe it's the number 10 or 0.01 or 1,000, and I'm just going to treat it as a constant in my equation. Is it a chain and product rule? Yeah, I guess so. I guess there's a tiny bit of product rule. I've got a k in here as well, haven't I? Yeah, minus k squared. Thank you, A, in chat. Aha, Herb's found some circles. Anonymous is doing Koschenscheinch with h's in them, in which case you don't get the minus sign. You're doing hyperbolic geometry. I'm not doing hyperbolic geometry yet. Yeah, okay. Good. Long story short, if you do y derivatives, you get back to, this is saying, if I really squint, this is saying you get back to a multiple of the function you started with. In terms of, you know, if you find these d squared, dx squared multiplied by c squared, if you find that scary, then you can imagine it's kind of a black box, right? Black box is this informal term for just complicated process, right? And I hope you agree that if we put y equals, change that. Back up. I hope you agree that if we put sine kx into the black box of differentiate it twice and multiply by c squared, oh my goodness, we get back some multiple of what we started with. Actually, I don't really mind if you accept it. I don't really mind if you agree with that being what's happening or not. So who knows about matrices? That's not. It's very tempting to go off topic and talk about how this shape. You have a black box operation. You put a thing into the black box. Black box does its maths and spits out, oh my goodness, just a multiple of the thing that I started with. You know, some of these, like multiplication by 3 is an example of that, where you put kind of anything in, the black box does its maths, and oh my goodness, we've got back a multiple of the thing we started with. In the world of linear algebra, so if you know anything about matrices, finding vectors that behave like this for your matrix is really important. They're called eigenvectors and associated eigenvalues. Oh, eigenvectors mentioned, linear algebra, actual, like, pure maths. This is an eigenvalue. If you know what that is. I am getting sidetracked. I'm going to go literally to the side. Quick spoiler for vectors and matrices. So if you have a matrix A, which looks like this, maybe your matrix is like this or something. Then multiplying by A, so x goes to AX. If you imagine that like a black box, then you can ask this question. If I put x in and get some multiple of my vector out again, can I have x goes to a multiple of x? And those vectors are really important for your matrix, because your matrix sees that vector, does its complicated multiplication, but effectively just stretches that vector by some amount. This is pretty important in analysing the properties of your matrix, in particular if you're interested in whether the matrix overall tends to be squashing or stretching vectors. That was a very vague way of describing eigenvalue analysis, but whatever. Yeah, so of course says, are you using some sort of differentiating matrix? And no, not really. I mean, I'm not seriously suggesting that this differentiation is a matrix, or is it, or am I? I think I'm suggesting that these processes have a very similar shape. There's something similar going on. I'm not suggesting that we think about it too much right now. I'm just sort of joking around that, that's kind of cool, isn't it? If you abstract things, yeah, this is kind of the point of the episode. I should probably do this bit properly. Hang on a moment. Yeah, okay, here's the message. If you abstract things, which means taking away the application, taking away the details of what you're doing, if you abstract things, then often quite different things end up looking remarkably similar. I'm trying to show you that on two levels. One, that behind things like water waves, on ripples on a pond, and waves on a string, or light waves, or gravity waves, behind all of that, if you take out some of the details, there's this underlying structure that's kind of similar to all of those problems. And at the same time, if you take that mathematical structure and you abstract more of the detail, so if you take out the information that it's something to do with derivatives, and you really like unfocus your eyes until it just looks like, we're looking for a function or whatever that comes back as a multiplication of itself. If you abstract that as well, then it starts to remind you of matrix theory, if you know any matrix theory. It's one of the nice things about, if you learn lots of sorts of maths, you eventually start finding connections between lots of different things. Should we get totally sidetracked? Don't think it is possible that matrix because it just scales the original vector in two axes. Yeah. So it's got this matrix I gave you. It's actually got boring examples. The answer is like yes. 1, 0 goes into my black box of being multiplied by the matrix and gives me back 2 times 1, 0, which is kind of boring. In general, it's a little bit harder to find these. What am I doing? I regret that. I want something like that. I don't know. The inverse problem of construct a matrix that has particular eigenvalues is actually easier, but somehow hard to do live. The same name to different things. That's a great quote. Right, we're getting really sidetracked for a second. Oh, I regret doing this. This is stupid. Okay, how does differentiation actually work? So when you learn differentiation, you learn that x to the n gets differentiated to give you n x to the n minus 1. So here the arrow means like just do some differentiation, like in school. You also learn that e to the lambda x gives you back lambda e to the lambda x, which is pretty, that's pretty exciting because it's just a multiple of the thing that you started with. That's pretty good. It's why when you see something with some derivatives in it, like this, when you see something with derivatives in it, a good idea is to try y equals e to the lambda x. It kind of, e to the lambda x respects differentiation in the same way that vector I showed you respects the matrix. It's kind of eigenvalues. The quote is from Poincaré. That's pretty good. Good, okay. If you use these polynomials though, if you use all of these for different values of n, then I suppose what's really happening when you differentiate a polynomial, so if you have something like 3 plus 2x plus 15x squared or something, when you differentiate it, what you end up with is 0 plus 2 times 1 plus 15 times 2x. And we usually write this out in a kind of structure like this, using plus signs and x's to represent the polynomial. But if we all just agreed to write our polynomials like this, 3, 2, 15, for what the coefficients are, it'd be a bit more snappy, right? To say, the coefficients are just this. We'll write zeros if we need to. Then we could say something like, well, this goes to 2 times 1, 15 times 2. And it's not too hard to turn this into a matrix. It's not too hard to turn the action of differentiating polynomials into a kind of matrix action. Right, we got really sidetracked. I need to come back to waves. If you learn how to differentiate e to the kx and x to the n, you differentiate basically everything because you can build stuff out of those things. Ooh, Jacob wants to know about log x, but I need to stop getting sidetracked and get back to waves. Whee! Okay. So sin x is really interesting because if you put it into these derivatives, you get back a multiple of itself. Also, what do I want to put in here? CKT is interesting because if you put it into d2y with a t squared, if you do two time derivatives on here, well, like yes, these constants c and k will get spat out twice as we do the differentiation. So the first time we'll get ck cos ckt, and the next time we'll get a minus sign from differentiating the cos, and we'll get sine again, and another ck. So we get minus c squared k squared y. So that's pretty interesting. We can combine these ideas together. So, if you take the product of these things, that's where the magic happens, I guess. If you take the product of these things, sine kx, sine ckt, then here's what's going on. When you try to do the x derivatives, then as you're doing the x derivatives, well, from that point of view, if you were told to differentiate this with respect to x, then you say, well, there's a lot of other letters of the alphabet around. I can see a k, a c, and a t, but whatever, let's do the x derivatives. And something like this will happen. You'll get back, I guess, c squared minus c squared k squared times the function. And on the other side of the equation, when you're doing the t derivatives, you'll look at this problem with fresh eyes. You'll say, this function y, I can see some t dependence. There's some other letters of the alphabet around. I can see c, k, and x, but whatever. I'm differentiating with respect to t. And when you do the t derivatives over here, you'll get minus c squared k squared y again. These derivatives are called partial derivatives. I suppose because they each contain part of the story about how this function changes. The idea really is that when you do these x derivatives, you ignore the dependence of the other input variables for your function. So you do these x derivatives pretending that t is being held fixed as a constant, just like we're pretending that k is fixed or c is fixed or something like that. And when you do the t derivatives, you pretend that x is fixed. So this expression at the bottom, we've got a solution to the wave equation. Better than that, because we've got this parameter k, which we could set to anything. Yeah, so good questions in chat, good questions. Does x not depend on t? For this problem, I actually don't think it does. X is my variable for how far along the string we are, which you can imagine being like halfway along the string. Does that depend on time? Not really. So I think x and t are kind of separate variables for x being how far along the string we are, and t being how much time has elapsed. So you can imagine asking, what's the displacement 3/4 of the way along the string at time 2 p.m. or something, and those kind of feel like independent numbers that you can change. Right, good question in chat. Why is that the wave equation? Where on earth did this come from, right? And I think I do need to defer that to university maths, I'm afraid. What I suppose I'll say is that the thing on the left with the time derivatives really is an acceleration. Just like in simple harmonic motion, you've got the F equals ma, you've got this acceleration of the mass. And the thing on the right is a force. It's complicated to derive that that's the expression for the force. It's force that comes from tension in the string. So this C is something to do with the string. It's something to do with the tension in the string. I'm aware chat doesn't exactly love physics overall as a group, so I won't say too much about the tightness that you've got on your string. Anybody who plays the guitar knows that you have those tuning bits, right, to tighten the string and change the change the tension in the string, which ultimately affects the waves that you get out of your guitar. Horrible introduction to the guitar. Yeah, how is that force when there's no mass? Yeah, good question. So this C squared is doing a lot of work. This C squared also contains. So I really did dodge the question about what's C squared earlier, right? Because C squared depends on many properties of the string. It depends on the tension of the string, and it also depends on the I want to say density of the string, or like the mass of the string overall, if you like. Guitar players know this because the different strings on your guitar are made of different stuff. Some of them are just heavier than others. So from maybe a physics point of view, there's lots of parameters that we should measure, like the tension in the string and the material it's made of, its material properties. From the mathematician point of view, these variables, so all the different things like tension and density, and I don't know, the strength of tension or whatever, they all appear in the same place in the equation. They all appear right here. Or I guess, if they're on the left-hand side, you can divide, so they all appear in the same place. And then you've got a nice level of abstraction, which is you can say, okay, we'll send the engineers off to go and measure these things about the string, about the particular problem, and then we'll combine them all together into the number C squared, and that's the only thing that matters. That's the only parameter in the wave equation. It's the only thing we care about when we're solving it. You know, if I told you that C is, it's not, but if I told you that C is like secretly A over B, where A is some weird bit of physics and B is some other weird bit of physics or something, then kind of none of that matters, right? It's kind of consequence free. It means down here somewhere you write, oh right, so the C in the answer is A over B. But you definitely shouldn't write A squared over B squared over A squared all the way through. That'd be way too much effort. It's kind of not obvious that there's only one thing that matters, but it turns out once you've done the linearization of the problem and you've resolved the forces, that there's only one place where those numbers appear. Counterintuitive. There's some amplitude around. Yeah, so I've got some amplitude which I haven't mentioned. All the way through, I could put a factor of 2 or 6 or 10 or any constant out here. Bigger waves. Okay, so this describes some waves. The fun thing, I think, is that if you want your wave, if you have a string or something which is being held fixed at the endpoints, so I'm imagining here a wave that's fixed, y equals 0 at the endpoints. Then if you've got these conditions on the endpoints, he says, drawing a very large endpoint, if you've got these conditions on the endpoint, that has an interesting effect on k. So far I haven't said anything about k, it's just a real number, that whatever k is, everything seems to be working so far. If you want your wave to have 0 displacement on the ends, perhaps because, I don't know, but on my commute there used to be this really long bit of rope marking, I think the edge of a sports pitch or something, and it was held up on 2 posts at the end. It's kind of fixed at the ends of the posts where it's tied to the post or something, but there's a long bit of string in between, and you could set up some really good waves going on the string because it's fixed at the endpoint, stuff going on in between. Yeah, suggestions that I use 2 pi. What do I think about this? Yeah, right, okay. I agree. I know where you're coming from. If that's sine x, then yeah, I should have written 2 pi. I'm about to make the point that that's not sine x. This is sine 2x. Right, here we go. So if you want this, then okay, let's have a look. So here's y, and it's already the case that if I put in x equals 0, I get sine kx is already 0. Great news. if I put in x equals pi, so this one is a bit, so I should plug in x equals pi, and I find that I want this. So we're asking for this thing to be 0, and I guess we're asking it to be 0 for all t, for all time. When I walk past this fence, walk past this rope at the edge of the sports pitch, it's not bouncing up and down at the ends. The ends are being held fixed for all time. Yeah. My k agrees with me for k equals 1 and k equals 2. Is k a multiple of pi? Yeah. So this works. You know, this sine CKT is not very helpful because it oscillates over time, right? It's a bit annoying. Sometimes it's 0, sometimes it's not. But we can have this. We can have this if sine k pi equals 0. So there's a question: when does that happen? When do we have sine k pi equal to 0? And I think that happens for k equals 1, 2, 3, and so on, counting numbers. Hi Fonzie. We're doing some waves. We've got some waves on a string. There's this thing where at A level you see some modes and harmonics, and we've just discovered that those are the ones with 0 at 2 given endpoints. That lots of things satisfy this thing called the wave equation in general, but only some of them have fixed endpoints. Yeah, wave equations, different equations involve both time and space. Nice. So these different harmonics. This splitting from up here k is a real number. Down here, k is 1, 2, and 3. This is called quantization. We say the problem's being quantized by imposing these boundary conditions. And so these boundary conditions are at the edges in space of the string. This one is at the left where x is 0, and this one over here is at x equals pi. I guess I've made the width length pi. Not much goes wrong if you make it a different number. That's how much string I would wanted to use. It makes the answer slightly more pretty, but not much goes wrong if you have a different length of string. So why is x changed to pi? Because I'm just looking at what's going on at this endpoint. We've got this blobby endpoint. We've got this kind of general solution, or general shape of things oscillating with different, if you know some language from physics, they're oscillating with different wave lengths and some corresponding frequency. But most of these are actually oscillating at random places. We would like this to be fixed at 0. Aha! Yes, I'm just super zoomed in, looking at what's going on at that other fence post. You know, it's like fence posts. How do you draw fences? That's not a fence. That's the letter H. But maybe people know what I mean. You've got these kind of fence posts holding the string fixed at 0 and pi. I'm zooming in on this one, right? It's not supposed to be wobbling at that end. Right. So physics people say a full cycle of the wave is 2 pi and a half cycle is pi. And I haven't helped matters. I haven't helped matters by drawing the k equals 2 mode on a string of the length pi. Yeah, okay. If you're worried about factors of 2, I don't think I've been very helpful. Yeah. So then these are called the I forget how the counting works, but yeah, these are called in some order the first harmonic, the second harmonic, third harmonic. I can't remember if they count from 0. I can't remember if k equals 1 means the 0 harmonic bass note. I forget the terminology, but yeah, these are harmonics. Quantization. Quant at the start of that word maybe reminds you of quantum theory or exciting things like that. And long story short, the wave equation also turns up not just in waves from a string, also waves from water, and also light waves, but also in some interpretations of it's called quantum theory, the kind of cloud of probability of where an electron is around an atom. So if you've got a hydrogen atom, there's certain probabilities that you find the electron in different places when you observe it. It's a really hard theory to get your head around, but seriously, that's what quantum theory is on about, I think. That equation also has some similarities to the wave equation, which leads to these sort of spherical harmonics for the probability distribution, and the quantization of those. So describing a much more complicated problem for electron probability cloud distribution. The energy levels for those are also quantized. They are the energy levels for those different electron shells that you learn about in chemistry. The ones where there's like 2 and then 8 at some point and then 18, and electrons can jump around different energy levels. They come from quantization of the wave equation in the same way that these waves on a string are quantized versions of sine kx. I just think that's really exciting, that two sort of completely unrelated bits of something you learn in physics with this kind of simple harmonic and waves on a string versus something you learn in chemistry about electron orbitals are secretly the same mathematics. Now maybe you don't care about physics or chemistry, but I still think that's a case for learning the mathematics, because then you can choose afterwards whether you want to use it to understand the kind of energy levels of a hydrogen atom, or whether you want to use it to understand something else, like fluid dynamics. Hello, Anonymous. Right, good. Everything is simple harmonic if you are brave enough. Right, good. Okay. I'll put some resources about electron orbitals in the further reading notes, because I don't think everyone's doing chemistry, and I think I'm excited about chemistry. I am excited about chemistry, so I'll put some notes in the further reading. There's some pretty cool animations on the web. It's really hard to do this in higher dimensions, because I'm already using 2, right? I'm using one for my space dimension, one for displacement. And I've got this time dimension as well that I'm not even really showing you. So just animating these things. Good, okay. So hopefully I've convinced somebody that there's some link between physics and chemistry and mathematics and maybe matrices as well. I've got 15 minutes. I want to mess around with the wave equation. I built a thing to try and understand it. Quick break while I drink a bit of water. Pi orbitals. I used to know why they're called pi orbitals. I don't know why they're called pi orbitals. Chat is maybe suggesting that they're called that because of maths. I'm going to put an ad on screen. This is a good one though. So this is Promise Europe is running again. Promise is a summer school. It's a very exciting summer school. If you're looking for a maths summer school, you might be interested in this sort of thing. Key features: it is 6 weeks long. It is challenging. It includes other people who are really interested in mathematics from across Europe, interpreted quite generally. And yes, Europe includes the UK for the purposes of Promise Europe. It's hosted in Oxford. It'd be weird if we didn't invite ourselves. It's for people who haven't started university yet and who want to do a summer school with loads and loads of maths. Really, I've seen how much maths they do in this summer school, and I don't actually think they could be doing more maths over the course of 6 weeks. It's amazing. Even if you don't want to do that, or if you're not in Europe, or if you're not age 16 plus, or if you're not pre-university, they have written a set of 8 problems at their website in the application section. So if you go to the application section for Promise Europe, there are 8 challenging problems, and I just think they're good problems. One of them's got a kind of monkey doing a Sudoku in it, so you can have a look at that one. I don't think we're allowed to discuss the questions in chat here, so I'm going to... Oscar's saying they've done some questions, and I'll allow that. I'll allow that, but I think we're not allowed to work together. Right, okay. Good. Okay, I really do recommend... Obviously, I recommend the concept of a 6-week maths summer school in Oxford. Hey, come and say hi. But I also do recommend having a look at their website just to download the PDF of some problems. Good. Somebody is in chat is friends with someone who went on Promise last year. And the pause was because I had to remember that it is now 2024. Right, okay. Promise. Waves. Okay, so quick recap. Ages ago, somebody talked about this travelling waves, right? They talked about the sum of some waves. Here it is. I've forgotten who said this in chat, but like the sum of some travelling waves. And there's some cool maths here, I think, for what happens if you add together waves. So if you add together, let's say, the bit of maths I need is, at some point you learn about cosine of A plus B and cosine of A minus B. I would like to add those waves. It's kind of like the shape. You can see why I want this, right? For the sine and cosine. You can see why I want something like this, right? With the like A plus and A minus. There are some expressions for these things that you learn in sixth form at some point, or A levels or equivalent. Yeah, there's some rules which give you this kind of cool fact. Let me write them out. If anybody at home is learning these rules live as I write them, I mean it's possible, right? It is available for people pre-university. So long as you haven't started a university course yet. So I think that includes gap year students. Yeah. I think the thing I'm getting at with this, by the way, is just that this is a cool fact that you take the sum of these two waves. So if I add them, then I get, I guess over here I get the sum of two waves. Are you ready for this? And on the right, there's some cancellation, and you get the product of two waves, cos A and cos B, multiplied together. So this, on its own, this is just a fact about angles, right? Like A and B are just boring odd numbers. But yeah, chat, you're correct, I should have done sine. I've hard committed because I've got a Desmos interactive that uses cosine. I thought I'd get away with the switch from sine to cosine, obviously not. Yeah. Thankfully people are going to uni in September. Yeah, I guess so. Pre-university, right? Yeah, I think that's correct. Don't see why not. Yeah. Okay. I was saying, sorry, this is about A and B, is usually just about angles, but with a bit of imagination, you can, if you take A to be something like, what if A is like m times x and B is like n times x, then we've got two functions. So if I substitute in, instead of A, I want to write like m times x, and I'm thinking about x being a variable, and instead of B, I want n times x. Then I suppose what you get is the sum of two cosine waves, now properly depending on x, is equal to the product of these two things, which is just really cool. Let me show you what this looks like in practice. I'm never sure if people see this, because I think, before I show you, sorry, I think when I learned these in the formula booklet or something, back when there was a formula booklet for A level, maybe there still is, these were just in there, and they were just, for me, they were just facts about angles. And I never once considered putting in functions of x. Anyway, maybe things are easier now that you can just stick them all in Desmos. Good, that's Desmos. Oh, I love Desmos so much. You get something like this. So I've got cos mx plus cos nx, which is slightly different m's and n's, isn't it? Let me fix that. So I think to be consistent, I should do this, mx plus nx, and over here, cos mx minus nx. Okay, oh, that's cool. Right, okay. So you see, you get this kind of product. Oh, look at this. I like this a lot. So there's kind of some outside wave and some inside dependence going on. Let's see if I make this. Yeah, so if I change these, that changes something about the sum of the two waves. So you can see this kind of longer behavior, sort of some local wiggliness, and also some sort of longer wavelength thing going on. Now I think with these, the interesting thing happens if I set n to be a very small number. So if n is a very small number, like 0. How small can I make this? 0.02. right, if n is a small number, then on the screen on the right, it looks like just cos 2x, right? Because who cares? Plus nx minus nx doesn't make any difference. But I think if I zoom out, yeah! Can you see that? I'm going to blow up the magnitudes just to make it easier to see. I mean, maybe you can already see what's going on, but yeah, if I blow up the magnitude, then you get something like this, where you get what looks like just cos 2x, I suppose, is very slowly changing in amplitude. That's the cos nx. That's very slowly changing that, like a kind of outside envelope of the cos 2x. So this says that if you take two waves with very similar frequencies, mx plus a little bit and mx minus a little bit, and you add them together, then you get something that kind of doesn't matter, right? They kind of play together nicely. Cos 2 and a bit x, cos 2 less a bit x, whatever. It's like cos 2x. But over a longer time, the amplitude squashes and comes back again. It's so good. Right, okay, let's it doesn't normally happen. Normally you just get something like this, which is some interesting wave stuff going on. And these are interesting, of course. There's a lot going on here. But as I make n small, look, you see you get these kind of long features. They get longer and longer because secretly here there's a product of two things. And one of those things is cos nx, which goes really long like this. In music theory, or in, I suppose, music theory sounds a bit pretentious. This is called beats. It's considered a bad thing. If you have two slightly out of tune oscillators, the sound that you get, rather than being a pure note, like cos 2x, you get something that you can hear it, the amplitude switching on and off, as if you've got something that's muting your sound wave. Over here, there's no oscillation for a moment, which sounds really bad. You've got two clarinets or something that are playing slightly different notes. It can be really bad overlap. This all goes away if one of the clarinets is much worse, then it goes away and you get something slightly different. You just get some sort of weird overtone thing going on. But you get this. I'm contractually obliged to mention dubstep at this point, because another word for what's going on here is low frequency oscillation. Let's break it down. Frequency is how often it happens. Low, not very often. And then oscillation, it's taking this waveform and oscillating the amplitude of that waveform. And if you set it up just right, then this can give you the kind of a note that pulses with its own rhythm, which is used extensively in electronic music. Good, right. Who'd have thought, right, that we could do an episode of Maths Club that tries to explain quantum theory and dubstep? We try to do both. Yes. Oh, there's an Arctic Monkey fan in chat. That's a much better reference. There's an Arctic Monkey fan in chat. Yeah, it's the thing from the album cover. Very good. Well done. Yeah, maths behind the double slit wave interference pattern. I haven't seen that for ages. I need to go and look up the maths behind the double slit wave interference pattern, because I can't remember. This is something to do with waves through a kind of double slit. I think I know what's going on, but only in quite a vague way. That the thing you're supposed to imagine is a big pool of water with two oscillators, but where the two slits are, these waves coming out and emanating in kind of circular patterns. There's your circle, I guess. It's not the right circle. These things spreading out in circle patterns and then having constructive interference and the other one, destructive interference, which is kind of what we've got going on here, except we're only in one spatial dimension, whereas I think the 2D slit experiment looks at how it spreads out 2 dimensions. I might be making stuff up. Okay. Right. Okay. I think I said that. I think I remember to say that's called beats, which is the important. Let's add a comment. Add a note. Beats. Good. Always save your work. Good. Okay. I think I'm close to wrapping up. I had other things that I wanted to do and show you and play notes. You get lots more fun by adding together different waves to try and build other things. These are really just the building blocks, or like the primary colours that you can combine together, because the wave equation is lovely. It admits these kind of basic solutions. No, they really are basic solutions. That's an example of a maths pun that is not going to work on. And never mind. It admits these basic solutions, but then it also admits lots of interesting combinations that you can take these things and multiply them by constants we said, and add them together. You can build other shapes of waves. It's really not the case that even the simple problem of just waves on a string. It's really not the case that it's just the basic low frequency overtones thing. Real twang on a string sets up lots of those different modes oscillating with different amplitudes all at once. And I think, depending on how much physics you do on this and how much maths you do in a related way, I think at some point you learn that people analyse the kind of harmonics that you get out of something like a clarinet or a piano string. The different harmonics within the note are different for different instruments, different for different ways of producing a musical note. It's very rarely that you hear just one frequency like this, just one of these modes. If you do, it's probably something like one of those electronic buzzers in DT, or it's probably like an alarm sound, or in the old days a computer beep noise, which just one frequency. You know it when you hear it, just sort of very clean and harsh. Whereas in reality, a piano or a clarinet doesn't sound like that at all. Oh, I lost chat for a moment, but I'm back. Thanks, Jack. Right, okay, I think... Oh, that is better than all of the puns I did. Right. I think it's 6 o'clock, which means it's time for me to wrap up. Thanks for watching this episode of the Oxford Online Maths Club. Each Friday we try to post further reading notes related to the episode. There's loads more stuff I could have said about waves. I owe you a link to some interesting wave orbitals for electrons. We post that on the Maths Club website, which is over at www.maths.ox.ac.uk/r/club. That's also where you can find links to previous episodes, recordings of this episode, and I will at some point, I guess, link to the promised place. It's where you can find out about James Street and the Mathematical Institute, who support the Oxford Online Maths Club. Requests, I don't think that's a request for headache-inducing noises, but I'll see what I can do. And a request for music, stuff about music. I've got a plan for an upcoming episode about harmonics and about intervals in music that I'm really excited about. Hopefully at some point in this term we get to talk more about music on Maths Club. But otherwise, I'll see you in 167 hours for another episode of the Oxford Online Maths Club. Have a lovely evening, and we'll see you next week. Bye.